Hello, everyone, and welcome back to M155 Mathematical Modeling. That's quantitative reasoning. In the previous video, we worked with frequency distributions, relative frequency, bar graph, and histographs. Today, we're looking at how graphs can sometimes create a misleading picture, even when the numbers themselves are technically correct, right? So let's jump right into the examples. And again, you can look at these terms. They're very easy to understand, and this is a very short, condensed version of them, okay? All right, so example number one, identifying a truncated axis. Okay, that's one of those terms. Suppose a graph shows approval changes from 48% to 50%. That's an increase of 2 percentage points. But suppose that the vertical axis begins at 47%, right? Instead of 0% because it starts at 47%. Now, the difference between 48 and 50% takes up a large portion of that graph. Visually, it can make, something like a 2% change increase look absolutely enormous, right? So numbers may be correct, but the scale exaggeration or the scale simply exaggerates the change. Okay. So always check where does the axis begin. Okay. So again, the graph approval changes from 48 to 50%, but it starts at 47%. Again, there's only a 2% change here. And the fact that it starts at 47, there's a huge gap between 0 and 47. So the visual exaggeration is going to be absolutely astronomical, right? Example number two, evaluate a pictograph. Okay. Suppose an icon represents sales, right? Twice as tall and twice as wide to represent doubled sales, right? The problem is that, pictures have area, right? So, an icon is, twice as tall. Suppose it's, this is it. And then suppose it's, the icon is twice as tall and then it says twice as wide. Well, you know, just to do it again, twice as tall. So this will be twice as tall and then twice as wide, right? Let's just, theoretically, right? Now, again, this is dealing with area, right? So area, we know area is length times width, right? That's the area. So if both dimensions double, then we would say, in the first one, right? Uh, we'd have this length times width. So I'm just going to say area one. We would just put A1 here and then A2. The area of two or area two would be essentially twice the length, twice the width, right? Or four times the length and width, right? So therefore, if A squared is equal to 4 times the length and width, we would say that the second area is equal to 4 times the area of the first one. Because remember, the first one is just length and width, right? So notice how I'm just replacing A1 with LW because that's essentially what it is, right? Area 2 is equal to, you know, 4 times the length and width, right? Area 2 is equal to 4 times the length and width, right? So the icon essentially is going to look four times as large as this one over here, even though the sales only doubled. So twice the height, twice the width is going to take up 4 times the area. And that exaggerates the actual change. Okay. So so four times the length and width is going to exaggerate the change, right? Because it only doubled. So a double is not, I mean, it's going to make it look like the change was astronomical. Okay. All right. Pause and try the problem, or you can do your corresponding problem either way. All right. Suppose a stock chart begins at a temporary low point and ends at a temporary high point. What effect does that have? So it can make the stock appear to have, you know, experienced tremendous growth, right? Which is what we looked at in the previous problem. For example, suppose the selected chart shows something like this. Suppose it shows, $40 and, $40 and $80, right? So the percent change, right, using the percent change formula, that would be 40, or excuse me, 80 divided by 40, or excuse me, 80 minus 40 divided by 40 times 100%, which is, that would be 40 divided by 40, which is 1 times 100%, which is 100%. Okay. And that sounds impressive, right? But maybe the stock was $90 before the temporary decline to 40, right? Maybe it was 90 before it declined, right? Because it says the stock chart begins at a temporary low and ends at a temporary high. Explain how the chosen window affects the story. Well, let's just say we got 40, we go to 40 to 80. Well, that looks impressive, right? Based on the percentage change. But suppose it was 90 first and then it went to 40, right? So if we use the larger time period and we say 90, and at the end of the day, right? Let's just say week 1 it was 90, week 2 it was 40, week 3 it went to this. So then when we compare the end all to be all with the percentage change, then we'll have 80 minus 90 divided by 90 times 100%. This will be 10 over 90, which is 1/9. 1/9 is 0.111. And that would be obviously negative because we'd have negative. So that'd be approximately negative 11.1%. Okay. And so all I did was basically, this was 0.111. So I basically just multiplied that by 100% so that I can move this decimal here. Okay. So same stock, right? But different time window. 100% increase versus, at one point, well, there was a steep drop here, right? So that shows a completely different story. That's why you got to always check what dates were selected. Okay. Example number 3. Here we are comparing absolute and relative scales. Suppose we compare two places with very different population sizes. One graph uses raw totals, right? One chart uses raw totals, and another one shows rates per 100,000. Okay. Which comparison is usually more appropriate, okay, for populations of different sizes? So the formula is basically, you know, rate per 100,000. Okay. So rate per 100,000 is equal to, the number of events. Okay. The number of events divided by the population. Okay. And then that's going to be times that 100,000 number. Okay. So suppose, city A has 1,000 events, right? City A has 1,000 events with a population of 1 million. Okay. So then, the rate would be 1,000 divided by 1 million times 100,000. Well, that would basically mean 100 per 100,000. Okay. But suppose city B has, and keep in mind this is just the rate over the population, right? Suppose city B has 300 events with a population of 100,000. So that's 300 divided by 100,000 times 100,000. Well, that would be 300 per 100,000. Notice the difference. City A, 100 per 100,000, 300 per 100,000. Okay. Looking at the totals, we got 1,000 and 300, right? 1,000 is greater than 300. But after adjusting for population's sake, we see that 300 per 100,000 is actually greater than 100 per 100,000. Okay. You got to keep that in mind, right? So raw totals can be misleading when the populations are different sizes. Okay. So you got to be very careful with that. But raw numbers still matter, right? Because raw numbers are definitely contextual factors. Okay. All right. Example number 4. Construct a fair graph. Okay. Suppose you're given a graph that appears misleading. How should you improve it? First off, clearly label both axes. So for example, if you have a graph, what I mean by axis is, I mean like this, right? So you have this and you have this. Let's just say, um, you have time and money. Um, and with respect to time, the more time you have, or excuse me, the more time, the older you get, you think the more money you make, right? That's how it should be. The more time you have, the more money you make, um, generally speaking. But describe how to redraw a misleading graph using labels, consistent intervals, source, time, and range. What I want to do is, suppose, for example, let's use, you know, let's use 0, 10, 20, 100, 200, right? Just for equal like spacing. The space should match the numerical difference. Okay. Next, I want to include like the units. Okay. Um, like the time period, the data source. Okay. Also use excuse me, make sure that the graph like provides enough context for the audience to understand what you're actually seeing, right? A fair graph should make it clear to answer like what's being measured, what units are being used, what time period is shown, where did the graph come from, and so this is why this makes sense, right? The more time you spend on a job, the more your salary goes up. Um, let's say this will be salary increase um, annually, right? Let's just say that's the title of your graph. Also, we could say, um, let's see, age, and height, right? Height, your height is going to increase with your age, right? Your height is going to increase with your age. And so this is why like numbers like this would be very appropriate, because it creates enough space in between so that you can distinguish between what's happening. So like, even if we were going from here to here, we would say, you know, how tall were you? Of course, this would be 0. How tall would you, when you were 5 or 10 or 15, 20, and then you would see, this would obviously be, a growth chart where you would basically, say what your height is here, say what your height is there, say what the height is here and here. And then you can calculate the in between, but you have to just make this make sense, okay? Whenever you're drawing a graph, you need to make sure that the labeling of it is consistent with what you're working on, okay? Common mistake. So a student says that if every number on the graph is correct, then the graph cannot be misleading. Well, that's absolutely false because a graph can use completely accurate numbers. Excuse me. A graph can use accurate numbers and still be misleading through things like what we looked at the very beginning, a truncated axis, where the axis is, the starting point is at 47 rather than at 0. You have, distorted picture sizes, selected time periods, poor comparisons, or even missing context, right? Let's say, all age groups are not being considered in the statistical study. There's a lot of different variables, right? So, truncated axis, distorted pictures. Okay, I see this all the time on X. I mean, time periods. I mean, there's a lot of different factors that could contribute to like misleading statistics. Okay, so you just got to be careful when people say, "Well, these numbers represent this." Well, there's more to the story. Okay. All right. So in closing, the main idea of this lesson is very simple: that you can have correct data, and correct data is not logically equivalent to a fair presentation. Okay. So we got to check the axis, we got to check the scale, the time period, the population size, the units, the context. Context matters before accepting a narrative. All right. In the next video, we'll look at correlation, causality, and confounding. Okay. Thank you again for watching, and I'll see you in the next one.